There are waves all around us. I don't mean the waves at the beach or in your hair, although they do count as waves, but rather I mean the invisible ones. The ones that heat up our food or help us see color. You could say there are invisible helpers. But enough praise for these waves. What are they? They go by the title of electromagnetic waves. Electromagnetic waves are crucial for our society, but there is one that has completely revolutionized the medical world. It has helped us look inside ourselves without any actual incision, just a snap and a flash. It's Agent RX, and welcome to episode 4 of The Next Prescription, where we'll be shining a light on the wonderful technology X-rays. We'll go over electromagnetic waves, what X-rays are, and then ride our way through their history, how modern X-ray machines work, and some potential advances being made. So if you're ready to see this remarkable technology in a whole new light, stay tuned. How exactly do these electromagnetic waves make up every color we see, let us heat up our food, or listen to the latest songs on the radio? In order to understand this, we must dive into the concept of electromagnetic waves. Electromagnetic waves are a form of radiation, which is the transfer of energy formed from one place to another according to the National Oceanic and Atmospheric Administration. They're formed when an electric and magnetic field combine perpendicularly to one another. One unique thing about electromagnetic waves is that they don't require any sort of medium. Most waves are classified as mechanical waves, like ocean waves, sound waves, and seismic waves, the waves that are produced by earthquakes. But they all require some sort of medium. Electromagnetic waves are different. They require absolutely nothing. They can travel through water and air, but they can also travel through literally nothing. They have the fascinating ability to make their journey across a space-sucking vacuum. Most electromagnetic waves are invisible, the only exception being visible light. So how can we differentiate between them? How does our microwave know it's receiving microwaves, not gamma rays? It all comes down to the wavelength. There is a spectrum of all the electromagnetic waves organized by the frequency of the wave's production. Each type of electromagnetic wave has a different intensity that helps us differentiate them from one another. Radio waves have the largest wavelength, lowest frequency, and gamma rays have the smallest wavelength, highest frequency. Even within a category of electromagnetic waves, the lengths differentiate. The best example being visible light, as red and purple can't have the same wavelength. They're different colors, so they deserve their own wavelength and frequency. Red has a larger wavelength and lower frequency. Purple has a shorter wavelength and higher frequency. The wavelength and frequency have an opposite correlation with one another. Understanding the difference in electromagnetic waves is not only important for individualizing the waves from one another, but also to recognize the difference in energy radiation. The higher the frequency, the more energy, and the more energy means the easier it is for waves to pass through denser objects. You can probably assume that X-rays are pretty tiny if they're passing through our skin. Now that we've built our foundation on electromagnetic waves, we can talk about the one with arguably the largest impact on the medical world, X-rays. X-rays are a type of electromagnetic wave with a wavelength range of 10 nanometers to 10 picometers. To put that into some perspective, compared to a regular meter, that is a range of 10 to the negative 8th to 10 to the negative 11th. Yet somehow, they are still not the shortest wavelength we know. Don't worry, I see you, gamma rays. X-rays' main purpose is to illustrate pictures of inside our body. From our lungs and muscles to our bones, X-rays help doctors discover and diagnose many problems, like confirming a fracture or detecting certain types of cancer. Doctors can analyze and separate different internal features on the X-ray images by looking at the changes in color. The lighter the figure on the X-ray means the more energy it can absorb, which means the material is denser. Bones tend to be extremely dense, and the X-rays struggle to bypass them, so they reflect back a wider image. On the contrary, lungs are filled with air and less dense, so the X-rays pass right through them and can barely reflect any light back to the image. The workings of X-rays is more of a physics concept rather than a biology one. One can't help but wonder how this mechanic made its way into the world of medicine. The person who figured that out must have really known what they were doing. Or they discovered it completely by accident. In 1895, Wilhelm Röntgen was experimenting around with the cathode ray tube. A cathode ray is just a beam of electrons. A cathode ray tube is a type of vacuum tube that emits fluorescent light when an electrical charge passes through. Previously, it had been discovered that when the cathode ray is met with an aluminum cover, it can pass through the aluminum. This is technically false. The X-rays were the ones passing through the aluminum, but at the time of the discovery, they didn't know X-rays existed, so they gave the credit to the cathode ray. The purpose of Röntgen's experiment was to observe the properties of cathode rays and fluorescence. As he was working, he decided to try and cover the tube with cardboard and only have the aluminum outlet remain uncovered. However, on the fateful night of November 8, 1895, while working in his lab, he noticed that one of the rays was shining through the side of the tube, even when the sides of the tube were fully covered with cardboard. Röntgen was shocked how his experiment returned different results than ones done previously. The difference was due to the phosphor used. A phosphor is a screen that is typically at the end of the cathode ray tube, but not always. Its job is to detect radiation by emitting light. Previously, phosphors of low mass were used. However, Röntgen used a barium and platinum one, which was able to detect the unknown rays, which he named X-rays, better and emit the light. The phosphor was not the reason as to why the X-rays were there, but it was the reason why Röntgen could identify that they were there. For the next 7 weeks, Röntgen studied many trials and experiments to uncover the properties of this mysterious ray. He found out that low-mass materials such as aluminum and glass produced less X-rays, while high-mass materials such as platinum produced more X-rays. You may be confused how the materials are producing X-rays, but don't worry, I've got you covered. It has to do with electron production, which I'll explain more in the How X-rays Work section. It is important to note that there are other factors too, such as atomic number, that influence X-ray production, but they were concluded by different scientists like Henry Moseley. Röntgen held up many materials behind a screen. From cards to books, he found out that to some degree all objects were transparent to X-rays. This enabled him to conclude that the density of the object has a direct effect on the transparency of X-rays. For example, tissue has a higher transparency, so it lacks X-ray absorption and darker images. While performing one of his trials, he found that his hand's bones were showing up on the projection. And then he developed the photo in the dark room, and the bones of his hands were still there. This led him to December 22nd, 1895, to take the famous picture of his wife's hand, also known as the first X-ray. After 15 minutes of taking the picture, it is believed Bertha Röntgen, his wife, exclaimed, "I have seen my own death!" Even though Röntgen was one of the main contributors to the discovery of X-rays, his work was an extension to the studies of Heinrich Hertz and Philipp Leonard, and after his paper was published, it let scientists around the world contribute to his discovery, from shortening the time to produce X-ray images to building modern X-ray machines. Röntgen is credited with the discovery of X-rays, but without help from the scientific community around the world, we would never have gotten to where we are today. Modern-day X-ray applications may be medical, but their whole foundation is physics. I mean, the discovery was due to a physics inquiry, so of course how they work is all physics. There are 3 main components to it: sourcing, accelerating, and decelerating the electrons. It feels like a negative concept, but the outcome is all positive. There must be an electron beam present in order for an X-ray to be formed. So step 1 of the X-ray machine is to source the electrons. This is typically done by a filament experiencing an electric charge. This causes the filament to get so incredibly hot that electrons start to get pulled from the surrounding metal, forming an electron cloud around it. Once the electrons are all cuddling together, they must be rapidly accelerated. This is accomplished by a negative charge, or the kilovoltage peak, kVp. It surges through the filament, causing the electrons to move to the other end of the tube. This is because there are 2 sides of the X-ray tube. One side is positive, the anode, and the other side is negative, the cathode. The sourcing of electrons is done on the side opposite of the anode, the cathode. Once the negative electric charge is distributed, the electrons have the energy to make their way to the positive anode because of the principle opposites attract and produce a high kinetic energy. With the high energy and strong attraction to the anode, the electrons slam into the anode wall of the tube and release their energy as X-rays and heat. This is what I was talking about, how the platinum produces more X-rays than the glass. It's because of when they slam into the platinum, it just is able to produce more heat due to atomic number density and other stuff. This is the deceleration step of the process. Fun fact, this principle was observed by our favorite Wilhelm Röntgen and allowed him to correctly conclude X-rays are a type of electromagnetic wave. X-rays are primarily applied in medical use. For example, simple X-rays like one of a hand or foot. CT scans, also known as computed tomography scans, which use computer processing and X-rays to deliver images that capture the body at more angles, creating a 3D effect. X-rays are even used for cancer treatment, known as radiation therapy, where the X-rays can damage the DNA of affected cells and tumors. Yet X-rays are also used outside the medical world, like airport securities. This technology is so remarkable, it is hard to believe there are no problems with it. Oh wait, there are. The main one being radiation exposure. When you're basking in the sun, the UV radiation from the sun's ray penetrate your skin and cause you to burn and become more prone to getting cancer. This is why we have developed sunscreen to help protect us from the harmful electromagnetic UV waves and radiation. X-rays follow a similar problem. Their high-energy rays give way to ionizing radiation. Ionizing radiation is a particularly harmful type of radiation that with prolonged exposure can impact the health of living tissue and potentially lead to cancer. Even though modern X-rays pose little threat to human health, the fact is harm can still be done, and it can't be ignored. Scientists, such as the ones in the American Chemical Society, ACS, are using their resources to try and eradicate this problem. They are finding ways to further reduce the risk of rays by simply creating less of them. However, this comes with a problem of sacrificed image quality. Despite these challenges, ACS is creating a way for less X-rays to be produced while not tampering with the image quality. They aim to do this by using a highly sensitive and foldable detector that will detect the fewer X-rays more efficiently and from more angles, so one X-ray goes farther. This advancement isn't just safer for humans, it's also safer for the environment due to less energy needed to produce the X-rays. X-rays may not be a new and emerging technology in the biological world, but it still deserves to show its light. To think how one of the most revolutionary technologies in the medical world came from an accident in a lab is pure luck on humanity. X-rays have allowed us to see our own death, as Bertrand Röntgen explained, but more importantly allow us to identify fractures and tears in our organs and bones, while also allowing us to detect cancer, one of the deadliest diseases in the world, at earlier stages, saving millions of lives. Even when not caught, it can provide treatment to those affected. There is no doubt that X-rays have significantly improved the life of humans all over the world. I hope this episode helped you understand the marvel that is X-rays just a little bit better. Please share your thoughts in the comments down below. I'd love to read them. Thank you for tuning into the next prescription, and until next time, this is Adrian RX signing out.